Hey y'all, welcome back. Today we're working on learning to solve equations using logarithms, and we are going to use some exponential properties as we go as well. So for this number one, we really want to use the one-to-one property. So we're going to try to rewrite both of these in terms of powers of 2. So 2 to the x is just 2 to the x. And 512 is equal to 2 to the, I'm going to have to, let's see, so 2, 4, 8, 16, 32, 64, 128, 256. So I believe that's to the 9th power. Oh gosh, I'm going to double check that, but I think that's to the 9th power. So yeah, let's just double check on that. Okay, it is to the 9th. Okay, good. All right, so yeah, we can rewrite this as 2 to the 9th. Oops. Wrong thing there. And so now we can use the one-to-one properties to set the exponents equal to each other, so we just get x equals 9. For number 2, we are going to use the looks like, well, we can add natural log to both sides, plus natural log. So plus natural log of x on both sides of the equation. And so we end up, when we do that, these cancel out, and then we just get a natural log over here. So what we end up with is natural log of 5 equals natural log of x. And once again, we can use the one-to-one property to say that 5 equals x. For number 3, we want to try to rewrite both sides using the base of 5. So 5 would be like 5 to the negative 1. And since we're raising that to the power of x, negative 1 times x is negative x, equals 5 to the power of 3. So it's a little easier, 5, 25, 125. So then we could use the one-to-one property and say that negative x equals 3. And so dividing both sides by negative 1, we would get x equals negative 3. For number 4, we are going to use the inverse property here by taking the natural log of both sides. Essentially what we're doing is this, although I typically, when using this property, don't write this step. I'll usually just skip to the next step, but taking the natural log of both sides is going to cancel out this base of e and just leave us with x. So x is the natural log of 13. And we can't simplify that anymore. That is irrational. So we're just going to leave it like that. For number 5, we will begin the problem by subtracting 5 from both sides, so we get e to the x equals 55, and then do what we did in number 4, take the natural log of both sides. Essentially what we're using here is we're going to invert, use the inverse function, use the inverse property to isolate x. So here the natural log of e is just going to cancel out and we've got x. So x equals the natural log of 55. For number 5, we will start by subtracting 4 on either side. So we get 6 times 2 to the t, thrown in a different variable there. Okay. We're going to subtract 4 from both sides, and so 11 minus 4 is 7. Then we're going to divide both sides by 6. So we get 2 to the t plus 5 equals 7/6. And gosh, I don't really like where this is going with the fractions, but let's keep going. Okay, so we're going to take log base 2 of both sides to get this by itself. Another way of thinking about it is just to rewrite it as an exponential equation. As a logarithmic equation. So we get t plus 5 equals log base 2 of 7/6, which I'm just going to leave like that. And then I'm going to subtract 5 from both sides. So I get t equals the log base 2 of 7/6 minus 5. And there's not really anything you can do about that. This is going to be irrational again. So I'm just going to leave my solution like that. You could type this into the calculator to get a approximate value, but I'm going to go with the exact number here. For number 6, we are going to treat this like a quadratic. Okay, so this is one of those problems. Go back to the lecture video if you want me to go into more detail on what's going on in a problem like this. But basically what we want to do is we want to factor this problem and write this as e to the x minus 2 and e to the x minus 1. Again, I go into more detail on this kind of a problem in the lecture video, so if you're kind of confused on the factoring piece here, go back and check out that video, and I go into, like I said, a lot more detail. So from here, we're going to set each factor equal to 0. If I can move this over. There's always something here. Okay, there we go. We're going to set each of these factors equal to 0 and solve them individually. So we'll have e to the x minus 2 equals 0, or e to the x, well, let me do a space here, will it? E to the x minus 1 equals 0. Looks like we're going to get two solutions here because either e to the x equals 2 or e to the x equals 1. And so when we take the natural log of both sides and apply that inverse property, we're going to get x equals the natural log of 2, or we get x equals the natural log of 1. Now that is something we can evaluate, so we can take this second solution one step further, because we know from our properties and just from our understanding of exponents that e to the 0th power is 1. So anytime you've got 1 in the argument of these logarithmic functions, it's always going to equal 0. So my two solutions here are going to be the natural log of 2 and 0. For number 7, we've got, let's see, what do we got here? We're going to subtract 6 from both sides. And so I'm going to have 3 times the natural log of x equals 4 minus 6, which is negative 2. Now that's throwing up a red flag to me. Actually, no, maybe not. Maybe we'll be okay here. Because it's not what's inside the parentheses that's negative. It's on the outside. And we can have, the range here is all real numbers. So actually that will not be a problem. We're going to divide both sides by 3, and I get the natural log of x equals negative 2/3. And then finally, I'm going to use the inverse property to rewrite this as x equals e to the power of negative 2/3. It is possible to rewrite this one when you have a negative exponent. If you're trying to rewrite it without a negative exponent, you would write it as 1 over e to the 2/3. And so this would be an acceptable answer as well. And if you really like using the square roots, you could write this as the cube root of e squared. But honestly, like, I think this is probably the cleanest way to write it, so I would just leave it like this. For number 8, so now we're going to be using, we're going to go back to the one-to-one property that we used in the beginning, where we can actually just drop both of these logarithms. And this is going to turn into a linear equation here. We've got 3x plus 2 equals 6 minus x. So I'm going to add x to both sides to get 4x plus 2 equals 6. Then I'm going to subtract 2 from both sides to get 4x equals 4. And finally divide both sides by 4 to get x equals 1. For number 9, we can't do that. We can't use this one-to-one property, because even if I were to subtract like this logarithm over here, I still have like the 2 plus. So what we have to do here is we're going to combine these logarithms using the product property. So we get log of, really what I guess we have here is 5x times x minus 1 equals 2. And then use the inverse. So we are going to rewrite this as like 10 squared. I think this may have been one of the problems we did in the notes. This looks kind of familiar here, to be honest. So, yeah, the numbers might be different, but I definitely recognize this. So, if you want more detail on what's going on here, just go back to the lecture video, and I think I break this down a little bit further. So anyway, here we're going to have 5x squared minus 5x equals 10 squared. Okay, so I'm just rewriting this. I'm using the inverse property to rewrite it as an exponential. Then I'm going to subtract 100 from both sides. I get 5x squared minus 5x equals 100. I can then subtract 100 from both sides. And I think what I might also do on this step, well, you know, maybe it's worth doing it as a separate step, but I might need smaller text here because we still have a few more steps left. But I'm going to divide both sides by 5. And so that's going to give me x squared minus x minus 20, which is going to be much easier to factor. So as I factor this, I get x minus 5 times x plus 4 equals 0. And so my two solutions, or at least potential solutions here, are going to be at 5 and negative 4. But as we saw in the lecture video, these logarithms have a domain restriction. So anything that you plug in to x, if it makes anything inside of any of these logarithms 0 or below, meaning like negative, then it's going to be an extraneous solution. So that didn't happen over here with number 8. You know, if I plug in 1, I get a positive and a positive in both of these, so this is going to be a good solution. But for number 9, plugging in 5 works, but negative 4 does not work. So negative 4 is actually going to be a bad solution here. It's going to be what we call extraneous. We're not going to include that in our solution set because it's not in the domain. It causes a domain problem, essentially, inside the logarithmic function. I'm just going to make a little note here that this negative 4 is extraneous, and we just need to be on the lookout for that moving forward, okay? We don't have to worry about that in the exponential equations because those don't have any domain restrictions. Let's see, I guess I neglected to check number 7, but this is going to be a positive number, so that checks out. Did I miss anything else? Everything else looks good. So this would be the first extraneous solution we got. For number 10, we're going to use the inverse property to rewrite this as 4x equals e to the first, which is really just e. And so when I divide both sides by 4, I get x equals e divided by 4. And that's it, okay? That is a positive number, so if I multiply that by 4, I shouldn't have any domain problems. So that's my solution for number 10. For number 11, I'll start by dividing both sides by 3. And so I get the natural log of 5x equals 10 thirds. And then rewriting this, I get 5x equals e, which is the base of the natural logarithm, to the power of 10 thirds. And then finally, I'm going to divide by 5. So this one's some of these solutions are just very strange looking, but don't let that throw you off. That's just what they are. Okay, we can't simplify it at all, so that's our solution right there. For number 12, oh yeah, and one last thing, this is positive, so plugging it into x here doesn't cause an issue. Positive times a positive is always positive. Don't really care exactly what it equals, as long as it's positive, we're in good shape. For number 12, we'll start by using the inverse property, rewriting this as, I'm actually going to rewrite it as x minus 8 to the 1/2 power, just because I know I told you all to, move away from using the radical symbol, equals e to the 5th. So from here, I'm going to square both sides to get rid of that 1/2 power. So I get x minus 8 equals e to the 10th. Squaring both sides does that. And then adding 8 to both sides gives me e to the 10th plus 8. Now if I add 8, subtract 8, I'm going to end up with just e to the 10th here, which the square root of that is e to the 5th, and natural log of e to the 5th is 5. All that checks out. So we're good. No domain problems or extraneous solutions here. For number 13, we are going to start by dividing both sides by 11. So we've got log base 3 of 0.5x equals 11 divided by 6. And then we can invert that. And we'll get 0.5x equals 3 to the power of 11/6. Okay, and it's okay to just leave it like that. Then we're going to divide by 0.5, which recall that 0.5 is really just like 1/2, right? So if this is really just like 1/2 x, instead of thinking about it as dividing by 1/2, let's think about it as multiplying it both sides by 2. So we're going to have x equals 2 times 3 to the 11/6. What a crazy looking number. I wouldn't even bother trying to go further with this. We've got the 6th root of 3, which is going to be irrational. This is not going to turn out to be rational anyway. So we just get this ugly old solution, but it is the solution. So there's number 13. For number 14, it looks like 14, 15, and 16 are all going to be problems similar to this one that we did in class, this number 6 here, where we're going to treat the function as a quadratic and then factor it as such. So here, we're using the e to the x as sort of like our x here. So we're going to factor this as e to the x. Let's see here. So two numbers that multiply to give me 6 and add up to -5 would be -6 and 1? No, -2 and -3. So -2, -3. So e to the x minus 2, e to the x minus 3 equals 0. And so we can split this up using the zero product property. So we're going to set either e to the x minus 2 equals 0 or e to the x minus 3 equals 0. And then we'll solve each one of these individually. We'll get e to the x equals 2 and e to the x equals 3. So my solutions will be the natural log, and we'll get these solutions by using the inverse property, but we'll have the natural log of 2 and the natural log of 3. We can't simplify either one of those anymore, so that's it. Those are our solutions. Now, our work for 15 and 16 is going to be very similar. Hey y'all, just wanted to give you a quick update on this number 15. Previously, we had e to the 2x plus 9 to the ex plus 36, and we saw that when you solve that, or you try to solve it, it's going to be something that's not factorable. You've got to use quadratic formula, and then I think you end up getting no real solution anyway. So I decided to change this problem so that this would be minus 36, and I think that's probably what I initially intended it to be. I want this to be factorable, and the problems that I'm going to give you that are like 14, 15, and 16, I think it's fair to say that you can expect them to be factorable. So I've already worked this out, but I just want to kind of talk you through it. Okay, the factors that would multiply to give you this trinomial are going to be plus 12 and minus 3. If you multiply those together, you get negative 96. Add them together, you get positive 9. And then you can use the zero product property to split these two up. And then you'll get either e to the x equals negative 12 or e to the x equals 3. An exponential can't be negative, as I've noted down here. So that's just going to be what we call an extraneous solution. E to the x could be 3, and when you rewrite that as a logarithm, the base is e, that's Euler's number, so that'd be the natural log, so x would be the natural log of 3, and that would be the only solution you get here. Okay, so I just wanted to insert this real quick, make that correction, and then we'll go back to the original video. So number 16, we've got, instead of e to the x being our term here, we just have 2 to the x. So with our coefficients being 1, 1, and negative 12. So this one can be factored. This one will be 2x, or 2 to the x rather. Let's see, two numbers that multiply to give me negative 12, add up to 1, would be 4 and negative 3. So we get 2 to the x plus 4 equals 0, or 2 to the x minus 3 equals 0. And while we will get, I believe we will get a negative solution here. Well, maybe we won't. Let's see. Let's see how it turns out. 2 to the x minus 3 equals 0. So here we'll get 2 to the x equals negative 4. And that's going to be a problem. That is outside of the range of the exponential function. And then we get 2 to the x equals 3. So if we were to use the inverse on both sides, we should know that we're not going to get a solution out of this because, you know, this exponential can never be negative. But just in case we didn't catch that, what we would say is log base 2 of negative 4 is x. But as we know, you can't input a negative number into the logarithm. So this is just going to be no solution over here. Okay, just nothing. Okay, and then over here, we do get a solution. We get x is equal to log base 2 of 3, which is a value. It does have a value. So just one solution on this one, x equals log base 2 of 3. Okay, number 17. Looks like we've got 2 logs on either side, but we've got some coefficient action going on both sides, so we do need to take care of that. Before we can draw these log base 2's, we're going to rewrite each of these logarithms using the power property. So I'm going to rewrite this one as log base 2 of x cubed, right? Using the power property, I can move that coefficient of the logarithm to be an exponent, equals log base 2 of 27 to the negative 1 power. All right. So at this point, I can just drop the log base 2's, and I'll have x cubed equals 1 over 27. And so I want to take the cube root of both sides, and the cube root of 1 is 1, and the cube root of 27 is 3. So we get x equals 1/3. Do a quick domain check, and we don't have any problems with that one. So that's our solution. For number 18, we're going to solve this one kind of like how we did, I'm pretty sure we did one like this already. Yeah, number 9, where we're going to combine the 2 logarithms on the left-hand side using the product property. But before we can do that, we do need to deal with this coefficient of 3. We are going to rewrite it using the power property. And so we get x minus 1 cubed. Oh goodness, this is going to be fun. And by fun, I mean I'm kind of dreading to see what's going to happen here. So it's times, or I'll do this in 2 separate steps. Log base 2 of 4 equals 5. Okay, so I applied the power property. Now I'm going to apply the product property. So I get log base 2 of this 4 times x minus 1 cubed equals 5. And I'm not going to bother multiplying this out yet. If I have to, I will, but I'm going to try to avoid it if I can. Okay, so at this point I can use the inverse property and rewrite this as an exponential equation. So this is going to equal 2 to the 5th. Okay, so a little simplifying going on here. 2 to the 5th. Let me just count my 2's real quick and see what that's going to be. We got 2, let's see, 2, 4, 8, 16, 32. So this would be 32. And if I divide both sides by 4, I'm going to get x minus 1 cubed equals 32 divided by 4, which would be, what would that be? Not 9, 8. Yes. And then at this point, I want to take the cube root of both sides. So yeah, this is actually going to pay off that I didn't multiply that out because the cube root of 8 is something that I can evaluate, luckily. So yeah, the cube root of 8 is just 2. So taking the cube root of both sides, I get x minus 1 equals 2. And then finally, adding 1 to both sides is going to be 3. Do a quick domain check here again. If I plug in 3 up here, I don't run into any issues, so that is going to be my solution for this one. Now with number 19, you might notice that the bases are different. We've got a base of 2 and a base of 3. So the strategy I like to use here is just take the natural log of both sides and then apply the power property to move those exponents down to be coefficients. So we got the natural log of 2 to the x equals the natural log, and you really could use any base you want. I just tend to use natural log because it takes fewer keystrokes here. But yeah, if you could use like log base 2 or something, you're still going to be stuck with an irrational number, which is why there's not a whole lot of point in trying to be too clever with that. Anyway, so now I'm going to move these exponents down to be coefficients, and that's using the power property. So x times the natural log of 2 equals x minus 1 times the natural log of 3. So next I'm going to have to use the distributive property and multiply this natural log of 3, which is just a single number, to both x and to negative 1. Okay, so I'm gonna multiply that in. So I get x times the natural log of 2. And I'm actually going to rewrite this. Maybe not. Maybe I'll just leave it like that. So equals x times the natural log of 3 minus the natural log of 3. So at this point, I need to collect all of my terms that have x over here on the left-hand side. So I'm going to subtract this term over. Remember that the natural log of 3 is just a number. It's nothing fancy or special about it other than the fact that it's irrational, but it works just like any other coefficient of x would work. So we're going to subtract this from both sides, and that will result in this. So x natural log of 2 minus x natural log of 3 equals the negative natural log of 3. Now I can factor out the x as a GCF. So I'm going to have x times natural log of 2 minus natural log of 3 equals negative natural log of 3. And then finally, my last step here is to divide this on both sides. So I'm going to get x equals negative natural log of 3. That's what I had over on the right-hand side, all divided by the natural log of 2 minus the natural log of 3. Now you could probably simplify this a little bit more, and if you used a different logarithm other than natural log, you may have gotten an answer that looks slightly different. But if you want to check to see if it is also correct, which it may be, what you can do is put this in the calculator and get a decimal equivalent and find out whether or not yours is the same. Okay, just test them both in the calculator, and if you did it correctly, you should get an equivalent expression. Number 20, we're going to solve this basically the same way as number 19. And 21 looks like it's going to have a similar strategy. So we're going to take the natural log of both sides. So we'll have the natural log of 3 to the power of 1 minus 2x equals the natural log of 5 to the power of x plus 5. At this point, we can rewrite the exponents as coefficients using the power property, very useful property. And so we get 1 minus 2x, this whole thing, times the natural log of 3. I'll even throw in a little multiply there to make that obvious, equals x plus 5 times the natural log of 5. Now from here, we want to do the same thing we did in the last one, which is distribute the natural log, this number, to both terms in the binomial that we are multiplying it by. And we need to do this on both sides of the equation. Our goal here is going to be to collect all of the terms with x on one side and all the terms that don't have x on the right-hand side. So that's kind of where we're going with this. So here we get the natural log of 3 minus the natural log of 3 times 2x, okay, equals the natural log of 5 times x plus 5 times the natural log of 5. So we get kind of a disaster here. And I'm going to just kind of rewrite this real quick with the 2. I'm just doing a little rearranging here and make this a little easier to look at. Okay, and so that looks okay. So now notice that we've got two terms that have an x. We've got this term, which is just like some number times x, and then we've got the one on the right-hand side as well. So I'm going to move these to the left-hand side, meaning I guess I don't really need to do anything with this one, but I need to subtract natural log of 5 times x on both sides to get it over to the left-hand side. Now once I got it over there, I'm also going to, and I'll probably do this in the same step, so do just a little rearranging, a little spring cleaning here, where I'm going to move natural log of 3 over to the right. So here's what I end up with. Negative 2 times the natural log of 3x minus natural log of 5x. So those two terms are on the left-hand side of the equation. And then on the right-hand side of the equation, I'm going to have, let's see here, 5 times the natural log of 5 minus the natural log of 3. Whew. Okay. I'm going to just kind of scooch this over a little bit so I can fit all this. Hopefully that's enough room for number 21. I might make these a little smaller if I have to. But anyway, so now I can factor out the x. So notice that this term has an x and this term has an x. So I'm going to factor those out as a greatest common factor. And I get x times, let's see, negative 2 natural log of 3 minus the natural log of 5. Okay, so this right here, it looks kind of crazy, but really it's just a single number. So it's just x times a number. That number looks pretty wild, but that's what it is. Same thing on the right-hand side. Like this is just a single number. We just haven't combined it or anything. We can combine it a little bit. I might do that towards the end. So 5 times the natural log of 5 minus the natural log of 3. I think I will try to clean this up a bit before we're done here, but I really want to focus on the strategy first. Lastly here, we're going to divide both sides by this crazy number, and that'll pretty much be it. The rest of it will just be sort of simplifying as much as we can here. So we get 5 times the natural log of 5 minus natural log of 3 all over negative 2 natural log of 3 minus natural log of 5. And I'm going to try to combine as much as I can here. I wonder, kind of going back, yeah, I could have combined a little bit here too. And I may go back and actually rewrite that. But here, so I'm going to use a couple properties, like for instance the power property, rewrite this as natural log of 5 to the 5th minus natural log of 3 over natural log of 3 to the power of -2. So that's really like 1/9 minus the natural log of 5. Okay, I'm going to use one last property here, I believe is the quotient property. Now if you get this far, I'm pretty happy with this solution, by the way. These next two steps really are not totally necessary. I'm just kind of curious how much, if at all, we can actually simplify this. So here we get x equals, and using the quotient property, we can rewrite this as the natural log of 5 to the 5th over 3. And I'm sort of officially out of room here, so I don't think I'm going to go any further. See if I can just like scooch this up a little bit. Yeah, I don't really see that there's going to be a huge point of this. So we've got 1/9 divided by 5, so that's going to be 9 times 5 is 45. So we get this, which, you know, I don't know that this is even really worth it, to be honest. I would just rather you leave it like this. Maybe like this if you really want to clean up a little bit, but this is getting a little crazy. So I'm just going to delete those. I was just curious to see if they would simplify nicely or not, but it turns out they don't. It doesn't simplify very nicely at all. So we'll just leave it there. All right, 21 should be solved similarly. So I'm actually going to make, well, let's see if I could just fit it. Let's see, I'm going to just draw a little line to help guide me here. So let's see here. All right. Now my first step is going to be similar to the last step, which is take the natural log of both sides. So get the natural log of 2 to the power of 1 minus 3x equals the natural log of 3 to the power of x plus 1. Is this not the one we just did? X minus 1. No, it's a little different. Okay. So I'm going to actually have to switch to a smaller font size here. So I get natural log, I'm sorry, we get 1 minus 3x times the natural log of 2 equals x plus 1 times the natural log of 3. I am going to distribute this natural log of 2 to both terms over here. Similarly, I'm going to distribute the natural log of 3 to both terms over here. So I get the natural log of 2 minus 3 natural log of 2x equals natural log of 3x plus natural log of 3. Yeah, I think that's it. Okay, so same deal as the last two problems. We want to collect our terms that have x. So I'm going to move this term that has x over to the left, and this term that has x I'm going to leave over there, and then the natural log of 2 I'm going to move over to the right. So I'll just do a little bit of rearranging here. So I'm going to move the natural log of 2 over here, and I'm going to move the natural log of 3x to this side. And so at this point, I'm going to divide both sides, or not divide both sides, I'm going to factor out the x as a GCF. So I get x times negative 3 natural log 2 minus natural log 3 equals natural log 3 minus natural log 2. All right, so at this point I'm going to divide what's inside the brackets over here on both sides. So I get x equals natural log of 3 minus natural log of 2 divided by the 3 natural log of 2 minus natural log of 3. And we can basically be done there. Again, you don't have to use natural log here. You can use any base. Sometimes, if I were to pick a base of 2 or base of 3, it might even simplify a little nicer. But at the end of the day, it shouldn't really make a difference. As long as this has the same value as what you got, you're fine. Okay, number 22, what we're going to do here is we are going to first combine those two logarithms on the left-hand side. The right-hand side, using the quotient property. So we get the natural log of x equals the natural log of 3 over x plus 5. And once we do that, we can now drop the logarithms using the one-to-one property. So you just have x equals 3 divided by x plus 5. Then we multiply both sides by x plus 5 to give myself x squared plus 5x equals 3. And if I subtract 3 from both sides, I get x squared plus 5x minus 3. And I don't think that has any factors. I think we either are going to get no solution here, or we'll get an irrational solution, and we'll use the So anyway, we're going to use the quadratic formula here. This is the bottom line. And we wrote it somewhere up here. I'll just copy and paste it. Yeah, here we go. All right, so there's the quadratic formula. So my b value here is 5, my a value is 1, and then my c value is negative 3. So we will get a solution here. 25 is bigger than 12, so we're safe in that department. So it looks like it's just going to be irrational. So 25, plus 12. Rather, not minus 12. This right here is going to be 37. And I'm just going to leave it like that. Those are our two solutions. Not much we can do. 37 doesn't have any perfect square factors, at least not that I can think of off the top of my head. So yeah, there we go. Negative 5 plus or minus the square root of 37 over 2. So there's two solutions here. Now, sort of the annoying part here is we do need to check, make sure we don't have any negative solutions here. I'm afraid we are going to have a negative solution. So I think what I will do here to really illustrate that is split this up and write this solution instead of using the plus or minus symbol, is to just write them separately. Write the two solutions separately and cross out one of them essentially. So we'll say this is the one with plus, and this is the one with minus. So really, we're just doing that domain check. We didn't have to do it on the last few because the original equations were exponential and not logarithmic. But here we need to make sure that we're not plugging in anything into x that makes the input negative. So if this is a plus, then this is bigger than 36, and the square root of 36 is 6. So this is going to be positive divided by positive is positive. So there you go. There's one of our solutions, or maybe the only solution, and I think so, because here we have a negative divided by a positive. That one is going to be, unfortunately, extraneous. So this one right here, we will delete. Okay, so this is what we call extraneous. All right, and there's the solution to number 22. Moving on to 23. Oh my goodness. What a behemoth of a question. Okay, well, we got a lot of logs. It looks like we can use those log properties, such as the quotient property here. So, and A doesn't even have a base. How annoying is that? Hopefully that doesn't cause any problems, but I think we're going to be in the clear due to our good old friend, the one-to-one property. So I'm not getting scared off by that log base A yet. I'm going to assume that it's just going to work out, but we'll see. You know, best laid plans, you know what I mean? So x minus 1 over x plus 6 equals log base a of x minus 2 over x plus 3. Okay, so now that we've got just a single logarithm on both sides of the equation, we can drop those and just set all the stuff in parentheses equal to each other. Oh, okay. Nope, that's not what I wanted to happen. There we go. So yeah, we can get rid of this log now. And we can get rid of this one as well. And now we got a little cross products going on. We're going to use the cross products property to, otherwise known as cross multiplication or the butterfly method, is to multiply the numerator of one of the ratios by the denominator of the other. So here we'll get x minus 1 times x plus 3 equals x minus 2 times x plus 6. So this is definitely going to turn out to be quadratic unless those x squared terms drop out, which actually I think they might. Okay, that'll be cool. So we get x squared, looks like plus 2x plus minus 3 rather, equals x squared plus 4x minus 12. So yeah, we can subtract the x squareds from both sides, and those will just go away. Now we're just left with a little linear here. All right, so what we can do here is subtract 4x from both sides, and so we get negative 2x minus 3 equals negative 12. Then we can add 3 to both sides and get negative 2x equals negative 9. And then divide both sides by 2, and we get 9 halves. So 9 halves is equal to 4.5, so I just want to keep that in mind as I'm doing my quick domain checks. 4.5 minus 1 is positive, this one will be positive, 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 so this is going to be a valid solution. And our only valid solution. So there is number 23. All right, looks like with number 24, we get a little bit of a reprieve here. One that's not going to take as much work to solve. So here, I think what I'm going to do is first rewrite this as x squared minus 1 to the 1/2 power, and then rewrite this using the power property as 1/2 times the log of x squared minus 1 equals 2, and then multiply both sides by 2. So just kind of simplifying that a little bit, doing a little trickery here to get rid of that square root. All right, now I can use the inverse property to rewrite this as x squared minus 1 equals, oh goodness, 10 to the 4th? You serious? Okay. Did I miss something there? No. Swear. Yeah. Okay. So I get x squared equals 10 to the 4th is 1 with 4 zeros. So if I subtract 1, that would be 9,999. And then I need to take the square root of both sides. I mean, my guess is that that's not a perfect square, but, you know, I don't know. Let's find out. Otherwise, we'll just say, you know, plus or minus 9,999. But I'm curious, as I hope you are. No, yeah, that's kind of what I thought. Not a big deal. So we're just going to get x equals, and we do get plus or minus. We don't actually have a domain problem here because whether or not let's say I plug in the negative root 9,999. Once I plug it in here, like the first operation that happens is I square it. So it's going to become positive either way. So I do get two solutions here, and those are my two solutions for number 24. Oh, you know what? I made a little mistake here. This should have been +1, not -1. So this should actually be 10,001. Yes, 10,001. All right. So there we go. There's number 24. Moving on down to the last page of the homework. This has been kind of a long one. So number 25, we're going to, looks like multiply the natural log of x minus 1 on both sides first so that we can try to get rid of those logarithms. We got natural log of x plus 1 equals 2 times the natural log of x minus 1. And now what we can do is we can use the power property to rewrite this as, or at least the right-hand side, as the natural log of x plus 1 squared, or x minus 1 squared. Now we can use the one-to-one property to drop those logarithms, and I get x plus 1 equals x minus 1 squared, which I guess I might as well square that out at this point. So that'd be x squared minus 2x plus 1. And now I want to try to move everything to one side and set it equal to 0. So I'm going to subtract 1 over and subtract x over. So I'll get x squared, negative 2x minus x would be negative 3x, and then 1 minus 1 is just 0. Okay, so this will actually factor a little easier than some of the other ones because all we have to do is just factor out the GCF, which is x. And so this will be x times x minus 3 equals 0. So either x equals 0 or x will equal positive 3. Now let's do our little domain check here. And let's see, let's put a little more space here. And if I plug in 0, I do run into problems with the 0. 0 minus 1 is negative up here. So 0, unfortunately, is going to be extraneous. And then 3, it does not appear to cause any problems. So there's our solution. All right, and this solution was extraneous, so I'm going to make a little note here. All right, and there's number 25. For number 26, what you have to notice here before you get started is you do not have the same base. So we're going to have to do a little base conversion on this one. A little tricky, okay? So just be careful you don't fall into the trap of just assuming you always have the same base. You got to keep an eye out for that. So what I'm going to do is I'm going to rewrite my log base 4 as a log base 2. So I'm going to rewrite it as log base 2 of x over log base 2 of 4. Now, I'm allowed to do this. What I'm doing here is I'm using the change of base formula. If you want a little bit more information about that, check out the lecture video where I go into a little bit more detail. But anyway, using the change of base formula, I can rewrite this as log base 2. Now notice I've got log base 2 of 4. Now 2 to what power is 4? Well, that's just 2. So this number down here is now just a 2. And so I can, when I'm dividing by 2, I'm going to actually rewrite that as 1/2 times. Okay? And the reason why I'm doing that is so that I can now rewrite this term. Like I want to get rid of this coefficient, right? So I'm going to rewrite this as log base 2 of x to the power of 1/2. And okay, kind of an interesting problem here. Let's see what's happening. So from here, it looks like we can use the quotient property. So I get log base 2 of x plus 1 divided by x to the 1/2. And that equals 1. And now I can use the inverse property to rewrite this as x plus 1 over x to the 1/2 equals 2 to the first power. Oh, wait. Yeah. 2 to the first power, which is just 2. From there, I can multiply both sides by x to the 1/2 power. So I get x plus 1 equals 2 times x to the 1/2, which is, remember, just square root of x. Okay, don't get lost on that. And then from there, I can square both sides. Okay, so this problem is just like getting all kinds of out of hand here. Yeah, so if I square both sides, oops, I'm going to get x plus 1 squared, which I will need to multiply out, equals 4 times x. So x plus 1 squared is going to be x squared plus 2x plus 1. Still got that 4x hanging out on the right-hand side, so I need to subtract that from both sides. And so I get x squared minus 2x, because 2 minus 4 is negative 2, plus 1 equals 0. Now I can factor. So yeah, this is actually going to turn out to be x minus 1 times x minus 1. So yeah, we don't need to check both of these factors separately because you're going to end up with the same solution. We're just going to get x equals 1. And let's just do a quick domain check back at the beginning. 1 and 1, either one causes a problem. So there you go, we get x equals 1. What a problem. Oh my goodness. Look at how many steps this one took. This one's ridiculous. Okay, good thing I left plenty of room for you on that one. Jeez. All right, last problem for tonight's homework. We're going to do kind of the same thing here where we got to do a little change of base action on this second logarithm. So I think what I'm going to do here is just copy and paste what I got over here, because it's going to be basically the same first step. So we get log base 2 of 3x plus 2 minus log base 2 of x over log base 2 of 4 equals 3 this time. So I'm going to do the same little trick that I did on the last one. And just like with the last one, I'm going to rewrite this as 1/2 log base 2 of x. So if you skipped over number 26, I kind of explain why I'm allowed to do that. So, all right, so now I can combine these using the quotient property after I rewrite this as x to the 1/2. In fact, I'll do that as a separate step. Use the power property to rewrite this exponent, or this coefficient as an exponent. And now we're going to use the quotient property. So we get log base 2 of 3x plus 2 over x to the power of 1/2 equals 3. Can use my inverse property to now rewrite this as 3x plus 2 over x to the 1/2 equals 2 to the third, which is just 8. I'll just leave it as 2 to the third for now. And then now I'm going to multiply x to the 1/2 to both sides. So I get 3x plus 2 equals 8 times x to the 1/2. Now I'm going to square both sides to get rid of that power of 1/2. Eight squared is 64, and x to the 1/2 squared is just x. So that left-hand side looks like it's going to be 9x squared, oh gosh, plus 2 times 3 would be 6, times 2 would be 12x plus 4 equals 64x. Then I'm going to subtract 64x from both sides. I'm really hoping we can get these numbers down a little bit, but I'm not feeling super confident. So we'll probably have to end up factoring this. But anyway, 12 minus 64. Do a little mental math here. 12 minus 64. So 64 minus 12 would be 52. So negative 52. All right, equals 0. Now, wow, we can't reduce anything here. This is going to be a disaster. I almost am on the verge of saying, hey, we should just quadratic formula this guy. I think. Yeah, I'm not even going to bother trying to factor it because this would be too big. I mean, coming up with factors of 36 that add up to negative 52, that's just too much. So I'm just going to bypass the factoring, and I'm just going to go straight to quadratic formula here. And if it turns out that they were rational values, then oh well, but I don't think it's really going to be worth it, to be quite honest. I think there's going to be too much guessing and checking here. So a little side note, here's the quadratic formula we're going to use. So I'm going to get x equals negative 52 would be 52 plus or minus negative 52 squared, which, what would that be? Let's see here. All right, 2,704. All right, so that's what we get right here. And then 4 times 9 times 4. So let's throw that in there as well while we're at it. Four times, let's see, A would be 9, C is 4. So we get 144. And 2 times 9, I think I can handle that as 18. So, all right. So here's my solution, or not my solution, but I still need to take this a little further. We need to do 2,704 minus 144. Okay, so if this number that I just got is a perfect square, then we could have factored it. So moment of truth here. I'm going to just go on a limb and say it's not factorable, but I'm not 100% sure. So it doesn't look like a familiar number to me, but you know, who knows? Okay, so it's not factorable, which is good news and bad news. Good news meaning we are effectively done. Now look at this number, 50. All right, so this number right here is going to be about 50. So even if we do the subtraction, let's go back to our original. We got to make sure that it's not going to make, if it's positive, it's absolutely not going to make either one of these negative. So I think we actually do end up with 2 solutions here. Kind of cool. All right, so there we go. There are 2 solutions. One's plus, one's minus there, but 52 plus the square root of 2,560 divided by 18, and 52 minus the square root of 2,560 divided by 18. That should be it for today. As always, please reach out if you want a little bit more help with any of these problems. But otherwise, y'all have a great day, and I'll see you next time.